Today, I'm going to talk about a couple of different subjects in the same presentation, and I think it will complete what the other presenters are showing. So it's I'm not sure I will cover everything that was mentioned by Megdad at the beginning, but I think it's going to be interesting to combine this information with the information presented by the following presenters. The plan of my presentation today, so I'm going to say a few words about the current code approach. It's my opinion, and I want to give a warning at the beginning that by no means I'm saying that we should not use codes. It's just that I want to put things in perspective that they may have some limitations. And in some cases, especially when we have very long service life requirements or very good concretes, as we find more and more today on projects. So I will say a few words about that, but the main subject of my presentation will be to talk about a couple of shortcomings of code approach. And I'm going to use a model to show what we can expect from different concretes that are compliant with the code but are different in composition, so we can get different durabilities or different expected service life. In my presentation, I'm going to use the stadium model. I know other presenters may use different models, so maybe the results will not be the same, but the idea is to show that you may get different things with different concretes that may all be considered compliant. And I will finish by a couple of examples where the code and the reality gave very different evaluations of the durability of a concrete element. So let's start now with what I consider to be the typical code approach. Codes were intended initially for structural calculations, not for durability evaluations. And durability is something that's been added to the main code. And I know that we're progressing a lot, but if you look at the different codes over the years, not maybe the last editions, but what the part of the code that's been devoted to durability is much smaller than what is about structural calculations. So sometimes it's just a few paragraphs, a table here and there, and you're expected to follow that and get durability results that are according to expectations. And it's based a lot on empirical knowledge. It's based on concrete properties that are not necessarily representative of durability first, like the water binder ratio or the compressive strength. And it's based on concrete properties that were measured over the years, let's say and it's based on experience. So experience is something we get from the past, but if we look at the current conditions or the types of concretes and the properties of the concretes that we can make today, it's much better than what we did in the past. So codes, because of that, codes may be too conservative in some situations, or not adapted to the concretes that we're able to use today for construction. So in the codes, usually you have the same pattern. So you have generic exposure classes, generic concrete classes, cover requirements. These are mainly the durability requirements that you get in the codes. They vary from one jurisdiction to another, but they follow some general guidelines. And codes assume that using the right concrete with the prescribed cover is assumed to provide adequate durability in a given environment. So if you take, for example, ACI 318 and you ACI 318 says you have chlorides, you do this, you do that, you should get a good durability. But there's no number, there's no fixed number of years that is attributed to following code rules. So it's the general understanding is that you get 50 to 75 years, sometimes 100 years with special provisions. The European code is clearer on that, so it's based on 50 years, and then you can increase to 100 years. The ACI, it's less clear. In the LFRD, you may get 75 years. So sometimes it's implicit, sometimes it's written clearly, but the expected service life usually ranges from 50 to 100 years when you, well, designers follow code rules. And the shortcomings of that is that there's no way of knowing the real effect of the environment with exposure classes. For example, once again with the ACI, you have the C2 class that relates to chlorides. But what does it mean? I mean, you may have different types of exposure to chlorides, but there's just one class. So, of course, if you design a concrete to resist chloride exposure, it's better if you know what type of chloride exposure you have, what's the severity, and then you may adapt the chloride, the concrete mix design to that exposure condition and reach the required durability. There's no way of knowing the resistance to external solicitation without any durability related requirements. So in the codes, sometimes you have a RCPT requirement or a diffusion or a migration coefficient, but in most cases, it's a compressive strength or a water binder ratio, and it's following that, it's assumed that you will get the required durability, but these properties are not durability related properties. So I know there are improvements that are being made to the different codes. Some are currently ongoing at the ACI, and it will be something that will be greatly improved in the future. But right now, this is something that is considered a shortcoming. The approach is not applicable for more stringent requirements that we see increasingly for new projects. So if you get over 50, 75 years of service life, then designers become more uncomfortable with the mixed design or with the durability design, because the code approach is good for something that is for a short service life, but when you get to things like 100, 125 years, then you're getting in an area, a gray area that is not necessarily covered with the existing codes. And all that being said, like for structural calculations, durability design requires a load-resistant approach. So you need to know what's the resistance of the concrete to the external solicitation, for example, chloride diffusion or the ingress of contaminants in the concrete, but you need to know as well the severity of the exposure. So this allows to make a good design. And on top of that, just like for structural calculations, you need to know the geometry and the characteristics of the structure. So what type of reinforcement you're using, what's the resistance of this reinforcement to the attacks like the corrosion, for example, what's the cover. So these are all elements that are important to consider in durability design that are not necessarily all addressed by the codes. And to illustrate what I'm saying, I'm showing you a graph here. This is taken from a database. So these are mixes that we have in we at SIMCO, we carry a lot of research projects. So we have a couple of databases with mixes made with different water binder ratios, different SCMs, different proportions of SCMs, and different age. of testing. So we used a couple of these mixes this information to build the graph that you're seeing. So for a mix with 54 MPa, for example, which is the average we get from those results, the diffusion coefficient may range from nearly 0 to, well, I'm talking about don't pay attention to the type of diffusion coefficient here because it's the one we use as an input in our model, but you can see clearly there's a large scatter in the diffusion properties for mixes that have comparable compressive strengths. And most of these compressive strengths are above 40 MPa, so which would be something like 3,500 psi, or between 3,500 and 400 psi. So it's well, sorry, it's higher than that. It's about 5,000, 6,000 psi. So it shows you that just specifying a compressive strength, you can get, you don't know what you're going to get in terms of durability. You can get anything depending on what's inside the mix and at what age it's tested, because some mixes develop their properties over a longer time than others. So just specifying at 28 days is not necessarily a good thing as well, especially considering the use of SCMs like we do today. Here on that graph, it's a relationship between the RCPT and the durability. So you see it's and the diffusion coefficient, I should say. So it's much better if we have RCPT. It's not perfect, but you see that there's some kind of correlation between the RCPT and the diffusion coefficient. So if codes incorporate RCPT requirement, it's better than just the compressive strength. But once again, if, for example, if you look at 1,000 coulombs, which would be considered a good concrete, and you see in codes that value 1,500, 1,000 sometimes, but you can still get a large scatter in the results in the diffusion properties. So as I mentioned, don't pay attention because it's the OH diffusion coefficient here, but it's directly proportional to the chloride diffusion coefficient. So maybe the scale is not something you're familiar with, but the scatter is still there. So it's the point is that if you're relying on compressive strength, you may get a wide scatter. If you're relying on RCPT, it's smaller, but it's still not a direct indication of the durability you may get. I'm going to show you an example here. So I decided to use a marine structure, and following a CI 318, this would be a C2 concrete that is required. It's exposed to moisture and an external source of chlorides. The maximum water binder ratio is 0.4, minimum strength 35 MPa. I converted in MPa. The cover is 65 millimeters for a corrosive environment. So there's a special provision for a corrosive environment. And I used also the European code. So based on these requirements, it would be an XS3 for a marine structure. And then I decided to use the tidal zone, because in the European code, the tidal zone is considered as a more severe exposure than the splash zone, than the submerged zone, sorry. So submerged is XS2 and tidal zone is XS3. So I decided to use the worst. The water binder, maximum water binder in that case, it's 0.45. The minimum strength is 35 MPa, and the minimum cement content, they have a requirement for cement content 340 kilograms per cubic meter, minimum cover 55 for that particular case, and this is supposed to give me 50 years of service life. If I want to go to 100 years, then the cover would have to be increased, but I decided to use the basic example. I picked 5 mixes in our database that would all be compliant with these requirements of these 2 codes. They all have a water binder ratio of 0.4, but different types of SCMs and different replacement levels of those SCMs, and they have all the same binder content. So I know you may think the binder content is low, but this was for a research project, and the binder content was kept constant for all mixes. So you may see larger binder contents in mixes with SCMs and mixes designed to get a good durability. In that case, the purpose was not to design, but to compare different mixes. So that's why they have all that binder content. Compressive strength at 28 days was always compliant with the requirements. The lowest that we get is 38.8 for a mix with 20% fly ash of type C, class C fly ash, sorry. And if you look at the RCPT, which is an indication of the chloride penetration resistance, you see that the mix without SCMs is much higher, almost 2,400 coulombs. But when you start using SCMs, you get much better resistance to chloride penetration. And we even have a mix below 400 with the one with 35% of class F fly ash. So these mixes would be considered, except the mix 1 that is made only with the type, which would be a type 1 cement, but we call it GU. It's worse than the others, but all the others would be considered durable mixes. I decided to model a caisson. The exposure is seawater with 34 ppt of salinity, and for the purpose of the example, I decided it would be in Los Angeles because you have a warm temperature and conditions that may be favorable to corrosion. The results that we get with the stadium modeling here, you have the chlorides expressed at reinforcement depth, expressed as a function of time. So the solid lines are at 50 millimeters from the surface. The dashed lines are at 75 millimeters from the surface. And you can see that based on the modeling that we did, none of these mixes get us to a corrosion initiation time of 50 years, and even less, 75 years. So the most that we can get is 30 years. And I decided the threshold would be at 500 ppm. It's not a strict calculation based on the cement content, but it's in the range of values that we get usually. And you can see that even if the threshold varies, it doesn't get us to 50 years. So, and that brings us to the definition of service life. So on this graph, it shows time to corrosion initiation. If you need a service life that includes a time to propagation, a time to damage, and a propagation phase, then you may add a few years, but it's not. I mean, you may get to 50 years, but it's a long shot to pretend that we can get 20 additional years after corrosion initiation. So this shows that by complying with that type of model, and the assumptions may be disputed. I know that that's one model among others, but I don't necessarily get to 50 years just by following the code approach. So we need to do something else. And that's why I was saying that we need to consider the exposure conditions, the site exposure conditions, and the local properties, and design concrete mixes based on that to ensure that we reach the desired service life objective. I have a couple of examples here I want to show. The first one is a cast pile that is exposed to groundwater. It was in Europe, so the applicable code was the European code, and the expected life in that case was 100 years. The specs were calling for moderate exposure. if we convert it to the exposure classes, for the worst case, it would be for that project, it was a XC4 and it required 40 millimeters of cover, but because of the uneven surface. Well, okay, I'm gonna jump just to show you that in that case, modeling after 100 years of real conditions, the cover requirement was 75 millimeters. What was specified was 90 millimeters, but I only needed 23 millimeters because the concrete was so good. It has a diffusion coefficient less than 1 × 10 - 11 square meters per second, and a high binder content, so a high threshold. So the real cover was much less than required. So we got a much better performance than if we were just following the code. The other example here is in Australia. I'm going to go fast. It was for carbonation. The required cover was 35 millimeters. I'm going to skip through that, but in reality, based on the concrete properties we were measuring that were much better than expected, we needed only 16 millimeters determined by modeling. And if we were using the conventional approach based on the measured carbonation at a given age, we were getting on average 19 millimeters. So modeling and the traditional approach gave much lower covers than what the code was requiring. So this is an important difference. And in that case, because you may end up with litigations if the bars are not placed properly. So it's better to check with the real properties and real exposure to determine what is really needed than just following the codes.